Okay, so this next topic, we're going to be looking at inequations and graphs. So a lot of it's recapping of ideas we've already seen. One of the more efficient ways of solving this sort of one is, rather than solving left-hand side is greater than the right-hand side, to try and solve left-hand side minus the right-hand side is greater than 0. Because this key idea here, remember, a function can only change its sign. It can only go from positive to negative in one of two situations. At an x-intercept, so when it crosses the intercept, it goes from positive to negative. But also it might be if there's a discontinuity in the domain. Over that discontinuity, it changes sign. I guess the classic example there is our hyperbola, y equals 1 on x. On one side of the discontinuity, it's negative. On one side, it's positive. But that's the only two situations it could possibly change sign. Recap on notation. So we use our brackets if the end point of the interval is included, whereas we use a parenthesis if the end point is not included. If both ends are included, we call it a closed interval. If both ends are not included, we call it open interval. And unbounded if it doesn't stop. It goes off to infinity in one of the directions. It's unbounded. So something like this. If x is greater than 5, we put it on our number line, we'd see something like that. That would be open because the endpoint's not included, but it's also unbounded because it's going off to infinity. In interval notation, we would write it like that. It looks like a set of coordinates, but it's not. We're talking about an interval there. And in set notation, we'd say something like this: all the values of x such that x is greater than 5, or something like that. This one here, now we're talking about something that's closed, but it's also unbounded. And we would write it that way. Then we might have something where it's between two values, something like that one. It's open because the endpoints are not included, but it is bounded. It does have a boundary on either side there. And the next one, difference there again is the endpoints are included. So this one's are closed, but again it's bounded because we've got boundaries on either side. Well, what happens if we have something like that, where one side is included but one side's not? We simply just say it's bounded. It's not open, it's not closed, because one side's closed, one side's open. So we just say, well, that's just a bounded interval. And what about if you've got something like this, where I've got two different bits? Well, that's just the union of two different intervals. That's how we would write the union of two different intervals. We also talked about composite functions. That's when we use more than one function to create some new function. So we substitute one into the other. We might substitute g of x into function x. Another way of writing that is using the open circle in between. It's not the letter O, it's actually an open circle. Sometimes people read it as fog because it looks like an O, but that's meaning that no, we're going to substitute g into f. Let's have a look at this one. If I was to find the fog of this particular one, everywhere I see an x, I'm replacing it with 1 on x squared. Let's tidy that up. There's our composite function. Whereas if I went the other way, which I guess we could say is golf. Now we're going to substitute this 2x on 4 minus x into the 1 on x squared. And there's no reason why they should be equal. And in fact, in the vast majority of cases, they wouldn't be equal. Let's look at solving some. So here we have this inequation to solve. It's already been factorised for us. It already has 0 on the other side, so it makes life nice and easy. I just pull out the critical points, the solution to it if it was an equation, and we get -3 and 1. And it's just a matter of testing the regions to see where we are. I could substitute points in if I wanted to. I could draw that graph. That's another way I could tell. But we end up with that. The big mistake people sometimes make with this sort of one is forgetting about the x equals 1 because it's a single point. It is part of the solution. So we've got x is less than or equal to -3, or it could also be x equals 1. That would be a solution as well. We've seen plenty of these, and there's all sorts of different ways of doing it. But let's look at the idea of let's pull everything to one side and make it well, in this case less than 0. If I turn that into one fraction, there we go. When it's that way, because remember we said it can only change sign when we have a discontinuity, well that would be the bottom of the fraction equaling 0, or at the x-intercept, well that would be the top of the fraction equaling 0. And that's why sometimes this is a nice way of doing it, because once you've got it as a fraction, to find the critical points, all you're really saying is, oh well, when's the top of the fraction equal to 0? When's the bottom of the fraction equaling 0? There are two possibilities here, are -3 and -13 on 5. It doesn't include the -3, because that's the bottom of the fraction. It can't equal that. And in this case, it also doesn't equal the other critical point, because the original inequation was just a less than. Let's see where we are. We test some points, and we find out, yes, we're on the left-hand side of -3. We're also on the right-hand side of -13 on 5. There we go. Okay, so there's a little recap on those sorts of things.